Hi everyone. So Agilan, could you see the lecture?
On YouTube, ma'am.
Yeah.
Yes, ma'am.
So there was a mishap last time, like since the tab didn't work, we pretty much had sort of a audio lecture. So just wanted to ask if you could follow or if you have some issues or some doubts, something.
No, ma'am. I couldn't check it fully. I just saw the video.
Also, shall we assume that you'll be able to understand today's lecture or not?
Yes, ma'am.
Okay. So anyway, like today's lecture is not going to be very much sort of off track or new material, but for the sake of sort of completeness for this particular unit which we started, we'll see what new there is to offer from the other book, which is the enumerative combinatorics. Okay. Yeah, please, all of you keep yourself unmuted so that we can actually have a discussion.
Okay, ma'am.
Okay.
Yes.
So maybe I'll share the book and we'll like quickly go through the contents of this particular book and see if there is something new which we should cover from there, and otherwise we can then like safely move to the next unit. I just want to make sure that you people are also comfortable with the other books, notations, etc. Yeah.
Yes.
Okay, so let me just open it in my end. Okay, is this visible?
Yes. Yes, ma'am.
Okay, so this is the book by Stanley, volume 1. Okay, enumerative combinatorics, and this is the part of the chapter which is supposed to be covered for the first unit of our current course. Okay, so initial portion talks pretty much about the same thing which we said while covering from the generating functionality, that whenever some particular recurrence relation is given to you and you want to find a closed form formula, you either want to find an explicit formula or you want to sort of estimate it or given asymptotic analysis for that particular function, right? So as an example, the first example, if you see, will my annotation work on this? So if you see, if this Fn is the number of subsets of 2 raised to n of the set n elements, then we know that Fn is nothing but 2 raised to n, right? And there is nothing like you would not agree to it. Similarly, if you have, so this is basically the derangement problem, that if you have n men and they have n hats and you have to give it back to them such that nobody gets their hat back, it's same as what you have always known as the postman delivering wrong envelopes to the houses, right? You know it best in that format. So that also, oh, this does not go this way. Okay. Any idea how these marks will be removed?
I think you have to erase it in Zoom thing.
Yeah, but if I stays in the annotation mode, page does not move.
If you do it in Zoom, it won't like
Okay, great.
change
Yeah.
along.
So this is that same problem, like stated in a different way, that you take n hats and you have to hand them back to the n men such that nobody gets their correct hat. No man receives his own hat. And that is exactly this number, right? So even though this formula is not as nice looks wise as we got in the previous one, but still we got a closed form formula and we are happy with it. However, if let's say later on, if I get a formula which looks simpler than this, then would you not be more enthusiastic to find out how I got the simpler looking formula?
Yes.
Yeah. And similar way, sometimes it may so happen that even though we have a closed form formula and which looks really complicated, and then at the same time we have a sort of formula which approximates the actual formula, but it is much more elegant and simple to understand and do analysis of. So then which one are you going to really pick?
Second one.
Second one. Even though it is not the exact formula, sometimes it's really a wiser choice to pick the one which is approximating it, if that is the one which is looking simpler, because then there are chances that we are going to get more information out of it. Okay, so this is what is being told in this particular example, that if you take all the n cross n matrices of zeros and ones, such that the condition is in each such matrix you have exactly 3 ones in each row and 3 ones in each column. So then how many such matrices are there of size n cross n is the number you have to find. So this seems to be the exact formula. How nice it is, no idea. But though we have a formula, good enough, but if at all we in some through some later analysis get, let's say, the formula to be this, even though this is not correct, we would be more inclined towards this formula, or if we get some estimate of it. Okay, same thing is here, that even though we calculate the FJs, and sometimes it is not so nice to get the entire formula by itself, but if at all you get to know that the approximate formula is there, you are more interested into the approximate formula, like this one. So an estimate may be given for Fi. So if let's say the indexing set I is n, this estimate frequently takes the form of an asymptotic formula Fn being approximated by Gn, where Gn is what? It's some familiar function. What's the advantage of this such a Gn? If you're working with a familiar function, you would know many more techniques to work with this, and you may have more information about such a formula. So you would know how to deal with it better. Yeah.
Yes, ma'am.
So these are the major reasons why people are not so fuzzy about the exact formula, but really about something which gives us more and more information and insight about the relation or the function that we are given. Okay. So after this, they start building the generating functions, which we already know. This is the ordinary generating function. This is the exponential generating function. We have talked about these things. Nothing new as such. And this is the notation which we know that an, so this particular square bracket xn of a function fx really denotes the coefficient of x raised to n in this particular power series, or rather formal power series, and that is nothing but the an, right? If fx was this. if fx was this, then you have to definitely multiply n factorial here, because coefficient of x raised to n here is an upon n factorial. So an upon n factorial is going to be this, right? And same way, you can deal with generating functions of several variables. This also we have done. We have done quite a few examples where we dealt with more than 2 variables, right? In one case, we even talked about which choice of generating function would be better for us. Remember, we had listed 3 types of generating functions. Let me just try to recall that through this. Is my new screen visible?
Yes.
Yes.
Cursor does not move for some reason. So I think this was in lecture 3, if I'm not wrong. So just to, so that you can also sort of relate to the current content, and then we'll feel more comfortable reading across the 2 books. Yeah, for this example only we had taken, if I'm not wrong. Here you see, these were the possible candidates. This was one particular generating function which dealt with 2 variables, and these were 2 sort of single variable, and then taking one particular aspect as constant, right?
Yeah.
Recall this particular example?
Yes.
Yes, sir.
Yeah, so now let's come back to the, oh, this is again not taking. Any idea how to come out of this? For some reason I seems. Yeah. Are you seeing the screen?
Yes. The book.
The book. Great. Okay. And similar way, so one would, really think that why do we even deal with generating functions when there is nothing but just the counting? If it is just a counting function. Reason, we already know that we can perform many operations on them. We can do addition of generating functions, we can do multiplication of generating functions, which is possible to, finitely many, not just 2. Any finite number of generating functions can be multiplied, can be added up, and then there was something like you had the unity, like you had reciprocal inverse, things of the kind. Let me directly jump to that point. Okay, so for instance, if let's say I want to ask that let this product be this, where alpha is some non-zero complex number, find out the expression, like what this Cn can be. So very quickly you can see if this is the product of series, this is the product of series, and if they are equal, when can they be equal? When they're equal component wise. So you do the component wise multiplications. I mean, you do the multiplication here. This is anyway like fresh series as it is. Collect coefficients of the same powers of x and equate them with Cn, right?
Yes.
So
Yes.
very quickly you can check that Cn is 1 only when n is 0. Because in that case, this particular thing vanishes and you get this 1. And for the other cases, you will have alpha n minus a power less here along with alpha here. But that is nothing but 0, right? Alpha n minus alpha n. Which means Cn is the series, constant series 1. All other powers of x are vanishing. So you can write this in this format. And therefore, you know that 1 upon 1 minus alpha x is nothing but summation alpha x raised to n. Right? We have used this like tons of times by now.
Yes, ma'am.
Now you can see also how it really comes very easily through all the things that we have studied in this course. Okay. Now, more examples. So this is again the same sort of example that you take two power series and then their product is the series 1, right? So everybody remembers this being written as summation 1 times x raised to 0 plus 0 times x raised to 1 and so on, right? This is nothing but 1 plus 0 into x plus 0 into x square plus 0 into x cube and so on. Correct? So this is actually this power series that we are dealing with. Okay?
Yes.
So then, of course, you can sort of keep on doing this calculation and figure out that this simplifies. Oh, I have to go to mouse. To this. For any complex number. Okay. Now, this we have already seen, so I'm going to skip this as it is. Now, something interesting which is new in this book is that if let's say you talk about the convergence, so in that sense of formal power series, the convergence is defined in terms of a concept called the degree of a non-zero formal power series. So if let's say the formal power series looks like this, so you have fx equals summation n greater than equal to 0 a n x n, then the degree of fx is the least integer n such that an is non-zero. Okay, the smallest number for which an is non-zero. So you can quickly verify that the product for the product formal series, formal power series, the degree is going to be the summation of the degrees of the two formal power series. And then it is quite straightforward to check that this Fix would converge if and only if the difference of the limits, like degree of the difference, that limit tends to infinity. Okay. Is this fine? So, I mean, maybe for notations, if you may have to go here. So if f1x, f2x is a sequence of formal power series, and if fx is another formal power series, we say by definition that f(x) converges to fx, written in this way, or the limit of fi is f, provided that for all n greater than equal to 0, there is number delta, and this epsilon delta definition, which you're like very much familiar with for the convergence, so that the coefficient of x raised to n in Fix is an, where an is the coefficient of x raised to n in the series fx. Okay. So component wise, if they are actually leading to the coefficients of this particular series, ultimately we say that this happens. Okay. You guys following me?
Yes, ma'am. Yeah.
All of you, all three of you?
Yes.
So after a certain limit, the coefficients of fi actually tend to the coefficient of x raised to n in f. That is when you say that the sequence of formal power series fi converges to the formal power series f. Okay, and that's precisely what is written here, that the coefficient of x raised to n in f1, then the coefficient of x raised to n in f2, this forms a sequence. This sequence converges to a constant value an. Stabilizes in the same manner, that after a certain limit, it becomes an itself. Okay. So equivalently, you would say that degree f is the least integer n such that an is non-zero, and then fi would converge if and only if the difference between these sequences, their degree tends to infinity. Okay, which means this sequence as a sequence becomes pretty much non-changing. Okay, and then Fix would converge to fx if and only if this degree is infinity, which means they eventually become the same. All right.
Yes, ma'am.
Like, don't get confused with this an non-zero. See, this degree is defined for this power series f, and then you're dealing with the power series fx minus fix. So this being zero, there is no so after a certain limit, it's really saying that the coefficients of this particular difference series is all zero, right? That's why there is no least for which it is zero, and therefore this limit is actually infinity, right? That is where we are getting that fi converges to fx. Okay. Some you're having some issue.
Yes, ma'am. This is fine. And also here that delta n, like it actually depends on n, right?
Right.
Yes. It doesn't mean the fi sequence will need not become fx eventually.
But after a limit, it really, stops changing. And that's how that delta n is determined.
Each coefficient, like
Sorry?
after limit, we for each n we will get a delta n such that after that coefficients will be the same for all the
Will be
further
same.
fi's.
Yes, yes.
Okay.
Okay. So with this, of course, similar way, you can provide the definition for the product of formal power series. And let's just not go into that, but these two things I will leave as quick exercises for you. Okay. So this will be, I should start annotating. This will be exercise and this will be exercise. So we'll come into the assignment sheet. Okay, I'll be releasing assignment sheet this weekend, possibly either by Friday or Saturday. Okay, and I'll keep it short so you can return it back to me in 5 days. Would that be okay?
Yes.
Yes, ma'am.
Was it like, I mean, the last time, did you find it lengthy?
No, it was fine.
Yeah, ma'am. It
I
was
think
fine.
more time would have gone just into the typing thing. I did not give any hard problems as such.
Yes, ma'am. The problems are not a problem. Only the typing.
So this
It
is
took
also
some.
a problem that the problems were not a problem. Huh?
So these two are there in the assignments. Is it, ma'am? Like these two
Yeah,
questions?
I will put them into the assignments.
Okay.
So this and this. Okay, basically this. They are very quick, like maybe sort of like 2-liner proofs. Okay. So yeah. Now moving further. Okay, so this is nothing but the same thing. This all analysis is the same. We have seen this. This also we have seen, if you guys remember. We did this, I think, just near the bell numbers. So maybe from there you can check this out. All this theory we have done. Formal derivative of a power series. And then all these you already know. Okay, this is something new. This we had not seen earlier. But g prime of x to be f prime x over fx. If fx happens to be a, so to say, quotient function, right? But that I think I can skip for now. Okay, so something the sort of other way around. You remember we did things like this. You start with this as a recurrence relation. You take this as your generating function. And then in your recurrence relation, you multiply the entire thing by x raised to n. And then add over from n greater than equal to 0, right? So if you do it with this particular term, you're going to get fx. Here you are going to get an minus 1 x raised to n. And then something, an minus 2 x raised to n. And then you add and subtract the other relevant terms and then reduce it to something looking like exactly, completely in the terms of fx. Okay. And this then finally yields the function fx to be 1 upon 1 minus x square. And this then you can use the partial fractions or whatever you want, and then you will have this as a proper series and you can compare the coefficients with this particular an to know the exact sequence, right? We have done this.
Yes, ma'am.
Okay, nice. Same thing here. So this particular one was dealing with the ordinary generating function, and this example is for the exponential generating function. Okay. So this is another example worked out for the exponential generating function. And this also we have done. So we should skip it now. Mobius functions के लिए there is a nice expression for the power series. Maybe good to read it up. Okay, for now I will skip because today's lecture I am trying to finish a little quickly. And then moving forward. So, okay, so something like this then. So this is another sort of quick way to do what we had done in the generating functionology, where we were trying to find the sum of the squares of first and natural numbers, and we said that we can do that if we know the answer to some another problem. Remember? Yes, people? Nobody is able to hear me?
We can hear you.
Nobody is answering me?
Like we wanted to find equated to some other series, and we want for which that finding the coefficients are easier.
Yeah, and why could we equate it to some other series? Because at certain level, it actually gave the answer which we were looking for, right? Not randomly.
Yes, ma'am.
So, excuse me. So that is what is happening here, that if you want to find the unique sequence of these AIs which satisfies this particular number, we have to see that this an minus k actually is the coefficient of x raised to n in this particular series. And we have done this. You see, this is nothing but the Cauchy's sum, right? an minus k.
Yes, ma'am. Yeah.
And since you're dealing with a and a, this means the two series which are being multiplied are the same series. Correct?
Right.
Yes, ma'am.
And those series are nothing but this particular series. Summation a and xn. So when you multiply summation a and xn with itself, the coefficient of x raised to n is exactly this. Isn't this true?
Right.
Yes.
Right? So these things are the coefficients of x raised to n in this particular thing. So then take the fx2 with this particular thing, take the product and figure out the things. Okay, and this entire business you can do on your own. You're pretty fast at this, faster than me. So that all is there. And yeah, these are when you see that the some function is evaluated when you really look at its derivative, right? When you shift the subscript by 1 in the ordinary generating function, formal power series generating function, what you get, remember from the earlier discussions, that's what is being happened here. So all those things are a repetition. It's good to go through it and get comfortable with these things. And Yeah, this is also routine. Okay, so far we have not really proved many identities, but in the maybe next lecture, so next lecture again will be a long lecture. We'll prove identities, or at least have a sorry, enough base for so that we can prove them. Okay, so one of the techniques is that whenever you have a certain set with a certain number of elements, and so there are many ways to actually show the cardinality of this particular set, right? And I guess computer science people are very familiar with these techniques, that sometimes you do this by thorough counting, sometimes you do it by listing out all the elements, sometimes you show that this set is in bijection with some other set whose cardinality we know. So such proofs, this particular technique of proof is the combinatorial proof or the bijective proof, because you show it to be same, having the same cardinality as some other set which has this cardinality. Okay, so what I'm saying is really this. So you have a set S and you have a set T. So this cardinality is what is unknown to you. Okay, or this is what you want to find, and this is known to you. Okay, if we can, or rather, if we can show that S is in bijective correspondence with T, then this will automatically imply that their cardinalities are same. Okay. And since mod T we already know, mod as in the cardinality of T we already know, we would know the cardinality of S. Okay. So such technique of proving the cardinality of a set is called a combinatorial proof or a bijective proof. Okay. So this is what is being highlighted. Okay. So, yeah, one nice example is if you would really want to say that, okay, n and k are two positive integers and you take k subsets of n, in how many ways can you form these subsets such that they do not intersect mutually. Okay, and then this thing also you can really prove the using the same techniques which we have developed earlier. You will have to build them from the smaller pieces where you know the information. You will have to put some of the, what do you say, initial conditions, and then some f of kn would reduce in terms of f of smaller values. Okay, and once you have things like this, you are like by now a master of how to deal with those things. All right, so same way, this is one identity which is really important. I think many of you would have it handy, like very quickly you can do this, especially I'm guessing people who have been through like who have in some sense some general idea of how all the Pascal triangles go. Okay, but this is really, really important, and this is going to be your another exercise. Even though its solution is already given here, I want you guys to do this so that it sinks in. Okay? Yeah?
Yes, ma'am.
Okay. Moving ahead, there are, oops. Okay, so this section is not an exercise for you, don't worry. Sets and multisets. How many of you are familiar with sets and multisets?
Multi-sets are sets where the same element can be repeated, right?
Right. Others have seen multisets?
I haven't seen much, ma'am.
Yeah, I too haven't seen much.
Okay, so then even though I have a lot of time left, I think I will stop today's lecture here, and we will resume on Friday.
Okay, ma'am.
Is that fine?
Yes, ma'am.
So this recording anyway I'll put on YouTube, and okay, so another things, if this works, can we delay the lecture timings by another half an hour? Will that suit all of you?
Yeah, I don't have any problem.
It's okay for me also.
Saham? Saham, am I audible? Oh, I think Saham has some connectivity issue today. Sorry?
I got disconnected. I couldn't hear that.
I was asking that would that work with you if we delay the lecture timing by another half an hour?
Ma'am, I have.
Okay, and Agilan, you were not there in the last lecture. I announced that we'll have our first quiz sometime in November.
Okay,
Uh,
ma'am.
Date is not, I have not picked up a date as yet, but sometime during the mid of November. Okay,
Okay. So the syllabus will be up to whatever you do before the quiz.
we will decide that.
Okay, ma'am. Yeah.
Okay, it's not so strict that it'll be till the lecture day. And because since we are already short of lectures, I will not keep it in the lecture time. I do not intend to keep a very long quiz anyway. So we'll figure out some common available timing, and then we will have a quiz at that time. Okay, it could as well be a Saturday, Sunday, it could be a 2 a.m. also, whatever works. All right.
Okay, ma'am. Yeah.
Okay.
How long will this be?
Not much. Since I have not prepared the quiz yet, I do not know. I mean, depending on what questions I put, I will have to see first for myself how long it should take for you to solve it. And then only I can decide the timing. But it will not be more than 1 hour for sure.
Okay, ma'am.
Okay, but it will be out of the lecture timings. I do not want to waste another lecture's time for the quiz. We have a lot of
Ma'am, did you upload the recording of the previous lecture in the YouTube playlist? I
Yeah.
couldn't.
It is not on the playlist, but
Yeah, it's not
channel.
on the playlist.
Oh, it
It's
didn't
the
go into
channel.
the playlist?
Oh, it's in the channel. Okay, okay. Actually, that's why I couldn't find it.
Oh, maybe it went into some other playlist or something.
Oh yeah, I got it in your YouTube channel, right? Sorry.
Okay, if that is the case, thanks for letting me know. I'll change the playlist. Possibly I put it in some other playlist. Maybe it went into my previous lecture. Mm. Oh, that's it. It does not show. Okay, so this I will change. And what more is there? Anything else to discuss? Yeah, your assignments. I'll upload back assignments on Friday. Okay.
Okay, ma'am.
Anything else? You have any questions or any suggestions how we can improve? If the speed is less, speed is more, anything changes you want to suggest?
Ma'am, did you provide feedback for the previous assignment, or I
Sorry?
was the previous assignment graded yet? The
No,
past
I
assignment?
said I will return back on Friday.
Oh.
So just check if it shows in the correct playlist now.
Oh,
The last
okay.
video.
Just a minute. Yeah. Yeah, it's there now. No,
Okay.
no, just a minute. I'm sure. Yes, it's there.
So some reason it didn't go in the correct this thing. I'm sorry about that.
So Friday we will be meeting at 6:30.
Yes, if Saham and I'm so sorry, I forgot the name itself.
Agilan.
Agilan. If Saham and Agilan are also fine.
Yes, ma'am, it's fine.
Saham has
And
also
Saham,
mentioned that he has.
yeah, Saham already said in the chat box. So 6:30 it is. Okay. Okay, okay. So today's lecture I'll end here itself. Friday we'll see counting problems and so if the speed is fine, I would like to really go a little faster than how we have been going so far.
Ma'am, like, can you tell us what you will be doing in the next lecture? So that
I would be really covering this particular chapter, more or less.
okay, like so that we can see before and we can go a bit faster.
Yeah. So that would be great if you can have at least a rough look of what content it is. You may not have to go into the details because what is more important I would emphasize in the lecture, and then it is a better idea to go into the details of those topics. But it would really be worth reading if you have seen it at least mota earlier.
Okay, ma'am. Yeah.
Okay, that way it will really allow me to move faster, asking you guys if you know this, know that, and then I can skip. This way, I mean, I have hell lot of stuff to cover. So I will pick up things from this which are needed for the current course and I'll teach. Okay, so I really have this Friday and at max next Wednesday to finish the current unit, and then I want to shift to the next unit. Although next unit pretty much is already covered, we have seen ordinary generating functions, exponential generating functions, worked with them well enough, right?
Yes.
So that way we are like the two units are covered simultaneously. but still a lot is left. And we
Past
have,
unit had more things like partitions, trees, and multisets, which we haven't yet covered. I mean, we didn't see anything about trees, right?
yeah, and those things, you know, to do those things, you have to first understand the generating functions, Riddhiman.
Okay,
And
okay.
that's how, you know, it's sort of messed up. That what you're supposed to do first is coming later, and then what you're supposed to do later has had to come first.
Yes.
So that's why now,
Unit 2 rather seems like it has been covered.
see, ordinary generating functions and exponential generating functions we have covered. We have seen all the operations which are there, the ring that they form, what all formulas we have, what happens when we shift the
Yes.
index. All those we have seen. That's what is the theory for the ordinary and exponential generating functions. Okay, don't pay much attention to the place where it says to be covered from so and so.
Yeah, chapter 3 it says. Of the
Don't pay attention to that, because if you see the chapter 3 of generating functionology, it doesn't really talk about these things.
Yeah, right.
So after we have covered certain topics from the enumerative combinatorics first chapter, both the unit 1 and unit 2 would be done.
Okay.
And then we can directly, I mean, in continuation, and this is the reason why I chose to first finish chapter 1 and 2 of generating functionology and then come to chapter 1 of EC, so that then in continuation of chapter 1 of EC, I can come to chapter 2 of EC.
Okay.
And there will be a smoother transition. Okay, and then it just, you know, same smoothly, it just moves to chapter 3. And after finishing that, we'll come to generating functionology, chapter 3 and 4, and we'll be done. Okay.
Yes, ma'am.
So that is the plan in my head. I mean, of course, you are more than welcome to suggest if you think of something else which can make the course better or the flow better. Ultimately, it should be more and more profitable to you. That's the main aim. All right.
Yeah.
So the sieve methods which you have, this is really the third unit. So we'll directly come into that after chapter 1. Okay. And after that, you have posets and these Mobius inversion formulas. That's chapter 3, which is the next unit, right? Here, not all of this we need to cover. Till here, we will have this. Okay, hyperplane arrangements we don't have to go into. All right. And of course,
Ma'am,
that's
like,
yeah.
do we need some basic number theory in chapter 3? Do they assume something? I mean, like,
If there is something which we would really need to do, then I would let you know.
okay, ma'am. Yeah.
Because possibly that is something which you would need once you start coming here. And we are not going to go into these sections. Okay,
Okay.
so that way I do not really want to bother you with the number theory as of now. If there is something, we'll see.
Yes, ma'am.
It doesn't seem to be coming, at least here, at least in the mota view which I am having. Okay.
Okay, ma'am.
Okay, so yeah, let's stop this here. Okay, so day after tomorrow, 6:30, right?
Yeah.
Yes.
Okay, chalo, bye bye.
Bye.